Well, I want to thank the organizers, Andrea Vitali, David Nilsson, and Fiorella Haini for giving me the chance of talking this and organizing, helping organizing programs. What I want to do during this 15 minutes is introduce you to our company, Lighting Cryogenics, and give you a very short introduction of how a dilution refrigerator works. How many experimentalists are in the room? Can you lift your arm? Not bad. Okay, so Lighting Cryogenics started 22 years ago while I was teaching at the University of Leiden. And I must say that at that time, industrial activities were not really stimulated, but people were not against. So we could start spending part of our time trying to apply things that I developed when I was passing my thesis in Europe in the 70s and the 70s. So this worked out fine. We have a company that makes the best dilution refrigerators in the world.
Actually, if you prefer, you can speak with the microphone.
The microphone. Yeah, so I would strongly advise the people at the university to stimulate young physicists who are doing experimental research to also spend some of their time, bringing to the people the results of their experiments, if it's possible, in the way of what people do in the States. So, a short introduction. Lighting Cryogenics has now 19 people, 4 physicists, 1 electronic engineer, mechanical engineers, 12. And it started in 1992. So these are assembly rooms with test machines. And we have, very recently, we started making the machines completely in our company. Before that, we used to subcontract parts of the machine. Now we are quite independent, and that's very good for production. So, how does a dilution refrigerator work? Anybody knows that here? Yes, all right. The fatter knows. Yeah. So the phase diagram of helium-4 is like that. You have here is pressure against temperature. You have the normal liquid. You have the vapor, and the melting curve that goes becomes flat at low temperatures. And this is the lambda line. So when you pump on a liquid, the cooling power at minimum temperature are proportional to the amount of atoms that you can extract. And that goes down exponentially with temperature. So in helium-4, you can reach 700 millikelvin, maybe a little bit less. In helium-3, which has a higher vapor pressure, you can go to 300 millikelvin. But then they stop, the temperature stops around that temperature because the heat leaks very quickly dominate, and you cannot extract enough helium from the bath. So nature gave us a very nice system, which is a combination of helium-3 and helium-4. If you mix helium-3 and helium-4, what happens is that part of the helium-3 goes into the helium-4 and stays there, energetically favorable, up to 6%. If you try to put more, it just phase separates out. And the funny thing is that the concentration is about 6.5% even at T equals 0. So you have this quasi-gas. You have normally, so liquid helium-3 is lighter than helium-4, so it floats on helium-3, and you have this gas below the helium-3, And the pressure of that gas is independent of temperature, and it's very high. It's about 25 millibar. So you can always remove helium-3 as long as you have a big pump. The amount of the cooling power goes down as T squared, not as exponential. So that makes the whole difference. And so instead of 300 millikelvin, you can now reach 3 millikelvin. So it's a factor of 100. So that's how it goes. So this is the phase separation. So you have a machine that you have built. It has a 3 Kelvin plate, then it has an evaporator, a set of heat exchangers, and a mixing chamber. And you start with a tank which has a mixture of helium-3 and helium-4, which you try to condense. In order to condense it, you have to put it in contact with some cold source. Typically, it used to be a pumped helium bath. It used to be a pumped helium bath. Nowadays, since 6 or 7 years, we have substituted liquid helium by a commercial post-tube refrigerator, which makes things much, much cheaper for in the long run, since helium is very expensive. And so this 3 plate is coated now so that your mixture of gas, in this case has 35% helium-3, can condense and then can fill up the whole machine up to a given level here in the still, which is where it evaporates. So that's what happens. The mixture fills up the refrigerator. Here you have liquid gas phase transition. And here you have a pump at room temperature that starts circulating this mixture. Because helium-3 has a much higher vapor pressure, then what you do is you distill helium-3 out of helium-4. And that's so the temperature goes down, and at this point, depending on the concentration, you get a phase separation. So one side is essentially low concentration of helium-3, the other side goes to extremely pure helium-3. And if you keep pumping, this is what happens. You get this 100% helium-3 and 6.5% helium-4. And here is your pure helium-3, this is the dilute phase. So when, it's very simple, when you try to pump out this gas, which has a high vapor pressure, helium-3 comes from the low entropy phase into the high entropy quasi-gas phase, and this produces cooling. So it's proportional to the square root of the temperature. So that's how the fridge works. It is normally made of a lot of vacuum cans, which keep the radiation low. This is the room temperature vacuum can, will be around here. And there's a 50 Kelvin shield and 3 Kelvin. And these are progressively lower and lower temperatures. This is the mixing chamber where people put their experiments. And what you want in a dilution refrigerator is a big mixing chamber. You can put lots of experiments. And you want a high cooling power and a low temperature. So that's what we try to do with this. The trick is to cool down the helium-3 that goes into the mixing chamber using the gas that goes out. The gas has a lot of entropy, so you can exchange energy from the upgoing into the so that is this is the helium reservoir inside the tanks. These are the pumps, and this is the new. It's the design of a new dilution refrigerator, which has the lowest temperature and the highest cooling power, and it has a huge mixing chamber of 35 kilos, where you can put 10,000 of wires. And most applications of these machines are for quantum computing nowadays, so people want, maybe hundreds of qubits and lots of wires. So this is a picture of the dilution refrigerator, the new version, which will be coming to Camerino also in the group of Ricardo Nathan. And two of those are also going to the University of Pisa, School of Milan. So the fact that the mixing chamber is very large, and you have here like 350 holes where you can fix your samples and so on. These are the heat exchangers that cool down the mixture coming into the mixing chamber. These are heat exchangers. And so the system is mounted in a sort of a table with spindles that lift it up so you can take out the cans. This is how it works. You can see the motors drive this down, and this allows you to change the various vacuum cans without having to use a lift. The pumping system is also quite new. We now use a magnetically levitated turbo pump that has no vibrations. Most of the concerns of people using post-heat refrigerators is that this vibrates. It vibrates much less than a different macaron because it doesn't have a mass going back and forth, just gas. But still, there is some concern, especially people doing optics and tunneling and so on. So we developed this pumping system. It has a very, very quiet primary pump pumping at the back of this turbomolecular. This magnetically levitated needs no maintenance. You can see here the difference between a conventional pumping system, which uses turbomolecular pumps, two turbomolecular pumps with a screw pump. This is the vibration on top of the gas handling system, and this is vibration on top of a magnetically levitated turbo. So this is very, very low. And there's nothing. No, it's all completely wrapped with super insulation so that the heat leaks go down. This is a graph of putting an accelerometer on the mixing chamber to see how low are the vibrations. You can see here. This is vibration on top of the cryostat. This is the vibration on the mixing chamber, the green one. So this is 100 nanometers. So that's extremely low. We also have the possibility of adding active dampers so that the fridge rests on these active dampers, and you can decrease the amplitude below 10 Hz by a factor of 10, which is important for tunneling microscopy. This is the cooling power. It's the highest in the world now. It's about 1.1 milliwatt at 100 millikelvin, and minimum temperature is 5.8. An important development is the top loading probe, because these machines take roughly 2 days to cool down, so you don't want to wait a long time. So when the machine is cold, you can put your samples on a top loading probe like this, which has mechanical contacts. When you pull on a rod, they expand and make contact to the various temperature plates. So this allows you to change samples in 3 hours instead of waiting a couple of minutes. So that's how it works. So you stop at different stages of the refrigerator, 15 minutes each, and then at the end you have your sample of the base temperature. This is the new refrigerator. It has a mechanical top loading probe, which has a very long bellows of 1.5 meters with more than 600 elements welded to it. And it is completely mechanical, so there's a motor that lowers it, and it's programmed so that it stops at different temperatures and terminals. This is the motor, this is the spindle that drives the motor. And here you can put your probe. The probe is something that you insert on the bellows, and you can mount all your samples, whatever, then you can change them very easily. You take one, put the other, and that increases the production. So that's how it works. You can see this is quite large now, it's about 8 centimeters, so you can put really lots of wires internally anchored in there. These are holes for temporary anchoring all the wires that go down, and this is a cold finger. Usually these machines can have very large magnets that weigh maybe 150 to 200 kilos. They go into this enormous cracking space, and you can do experiments in fields up to 15 Tesla. So this is how you operate your refrigerator. This is an animation that's on our website. And the probe. I think that's all. Thank you very much.
I don't see any direct questions, but I think during the coffee time there's ample time for asking maybe financial aspects. Okay, so I would like to thank all the speakers, and especially the animated question time, which was in each time too short. So let's thank all the speakers.